This is the second video over Chapter 10 for the AP exam. Here I'm going to look at the very last page at some free response questions that are more lab-based. These come pretty often on the AP exam. Let's go and work through one of them. So 28. We have an equation that represents the decomposition of a compound containing an unknown element X. Notice here it is. We don't know what this is. There is no element with the symbol X on the periodic table, so we'll have to find that out. A 139-gram sample of it was completely decomposed by heating. The gas produced by the reaction was captured over water and collected in a gas collection tube at 24 degrees C. The total volume of the gas was 506 mils, and the total pressure inside was determined to be 738.5 torr. They also give us the vapor pressure of water. Now, if you recall, whenever you collect gas over water, you have to consider the pressure inside of the gas. So here is a container that's a gas was collected. This is our gas that was collected over water. Part of the pressure of the gas in here is due to the vapor pressure of water because it was collected over water, so water actually contributed some of this pressure. The water essentially evaporated. Above any sample of water or any liquid, you have a vapor pressure of that liquid. That's what they give us here. So we'll actually have to subtract away the water vapor pressure from the total pressure before we can do any PV and RT type of calculations. And that's what Part 8 asks us. Calculate the partial pressure and torr of the oxygen gas that was collected. Now I should say not all gases can be collected over water. Gases that will not dissolve in water appreciably can be collected. Oxygen is not very soluble in water, so oxygen can actually, you can do this with oxygen because oxygen is nonpolar and water is very polar. Right, so to get the partial pressure of oxygen, we have to subtract away 738.5 minus 22.4. This shouldn't be too bad, but you can go ahead and use the calculator for this section, but you get 716.1 torr. Make sure you label your units for any number you put down. And make sure you follow significant figure rules. We go to the first decimal place because we're subtracting, and so that should work. Notice my total is 4 significant figures, even though I have 3 here. That's because I use the subtraction rule for sig figs. B says calculate the number of moles of O2 that was collected. So this is simple PV and RT, since we have all the parameters needed, and we're collecting oxygen gas. So PV and RT, we want to calculate moles. We want to solve for N. N then is PV over RT. R is given to you in the equation section, so we're good there. Now the pressure has to be in atmospheres. Because R, the constant R, remember, is liters, atmospheres, moles, Kelvin, all the units have to match up. So actually we have to be in atmospheres. So we can divide the pressure, we can convert this pressure into atmospheres. To do this, we'll have to, 1 atm goes on top, and 760 torr in 1 atm. This conversion factor would also be given to you. So is it okay if I just do this since we're dividing? Can I just do 716.1 over 760 as my pressure? Is that fine? My volume then would be, has to be in liters. Notice I have to have liters. So I have 506 milliliters, which is 0.506 liters. My R is on a constant, 0.0821 liters, atmospheres, moles, Kelvin. My temperature is 24 degrees Celsius. So I'll have to convert this into Kelvin. Again, notice every unit had to be converted. So in Kelvin, I add 273, which gives me 297. Right, so a little bit of conversion. Every single parameter had to be converted. But if you do the calculation, you should end up yourself with 0.0130 moles. Oh, I'm wrong. That's actually the next answer. This is 0.0196 moles, a little better, of O2. Make sure you label your units once again. Now they ask us in part C to determine the number of moles of XClO3 that was decomposed. So since we have found out using PV and RT how much gas we collected, we can now backtrack and find out how much original solid we had. This is a little bit of stoichiometry. So we know that we're beginning with 0.0196 moles of oxygen. Stoichiometry tells us we want to go from moles of oxygen into moles of our compound, XClO3. The relationship is 1 to 3 seconds. seconds. Now, I don't know if you've ever done 3 seconds, but you could put this in stoichiometry definitely. And if you do this in a calculator, if you have trouble plugging this in, I am thinking of it as dividing by a ratio is the same thing as multiplying by its reciprocal. So I'm thinking about times 2/3. That's what I would do in the calculator. So we actually should, this number should come down, and this number comes down 2/3 to 0.0130 moles of XClO3. Right. Now, real quick, the X, just a little note, is probably an alkali metal. How do I know if it's an alkali metal? Actually, it doesn't have to be. No, it doesn't have to be an alkali metal. Never mind. It could be from the G block with a +1 charge. But we know it has to be a +1 charge. That's what I was thinking. +1 is probably going to be the charge of this because this is chlorate. Chlorate has a -1 charge. But it's likely going to be an alkali metal. So we'll take a look. Now we want to determine the molar mass of the compound. Since we have ourselves the moles, since they give us the original mass, 139, molar mass is grams per mole. That's what the periodic table numbers give us. So my grams is 1.39. My moles is 0.0130. When I divide the two numbers, I get 24-ish, 23 or 24, depending on how many significant figures you use. So about 23. And I think if you use more significant figures, you'll get a number closer to 23. So I can actually see that this matches up very closely to sodium. Good old Na is 2299. Right. So I bet this is sodium. And that's what the last question asks us. Determine the identity of element X. So this is grams per mole, which comes from the periodic table. So identity of element X is all right, sodium. There it is. All right, so be prepared to do a question like this. Let's set up, I won't do the whole question because I want you to practice this sort of thing on 29, but let's set it up. 29 is another experimentally based PV&RT question. And here we have ourselves a student was assigned the task of determining the molar mass. Again, very common calculations with gases is to get the molar mass of an unknown gas or a compound. The student measured the mass of a sealed 843 milliliter rigid flask that contained dry air. The student flushed the flask with the unknown gas, resealed it, and measured the mass again. So we're beginning with a flask, an empty flask, and we're taking the mass of it, so we can get the grams of the air in there, and then we're flushing it with the gas and measuring the mass again. And notice here are the measurements. The volume of the flask is 843. The mass with dry air. Now you can't have nothing in the flask, so the student, you can vacuum it, but that was not the procedure. We have air in here, and then this is the mass of the gas when it was flushed with the unknown gas. Both the air and the unknown gas were at 23 degrees Celsius, 750 torr. Get prepared for PV&RT. That's why they're giving you all these parameters, including the volume. The data for the experiment are shown on the table on the right. So they want first to get the mass in grams of the dry air that was in the flask. The procedure is this. If you can find out what the mass of the dry air was, gram of air, then you can subtract away the gram of air minus the total here, and then get the mass of the flask. If I can get the mass of the flask, then I can find the mass of the unknown gas. So let me say that again. You would first get the mass of the flask. The way you would do that is by finding the mass of the air and subtracting it away, because this is the total of air plus flask. So if I can get the mass of the air, I can subtract it from the flask. Then this is gas plus flask. So I can subtract away the flask and I'll get the mass of my gas. And I'll only do part A here, but part A actually tells you to get the mass of the air. So then you can subtract away the air, get the mass of the flask, subtract away the flask, you get the mass of the gas. Now here they tell us the density. Here they say that the density of air, of dry air, is 1.18 grams per liter. This actually says per liter. Grams, L to the negative first means grams per liter, at 23 degrees Celsius. So we're going to use density. Remember that density is mass over volume, And density is a way to convert between mass and volume. So if you know volume, you can get to mass if you have density. That's exactly what we're doing. Our volume is actually 843. So that's milliliters, and our density is given to us in grams per liter, so we can convert this, if you'd like, into liters. This is 0.843 liters. And let's solve for mass. We would move the volume this way. We've got volume times density equals mass. So our mass is 0.843 multiplied by 1.18 to get us a mass of 0.995 grams. So this right here is the mass of air, dry air. So go ahead and continue the problem by subtracting the dry air from this. You'll end up with the mass of the flask. Subtract this minus the mass of the flask. You get the mass of air. And you can get B, you can get C, and on down to D. All right? And we will take questions in class.